Hey everyone, welcome to this explainer. If you write in C++, you have probably hit that wall where you're just typing the exact same logic over and over again. Well, let's fix that today. We are talking about C++ templates, basically your magic wand for turning messy, duplicated code into sleek, automated brilliance. So here's our roadmap for this two-part deep dive. We'll start with the code duplication headache, introduce templates, and then break down function templates, class templates, and finally, how to actually compile all this stuff.
All right, let's jump right into part one, the code duplication problem.
Look, if you've ever messed around with function overloading, you know the absolute grind I'm talking about here. Say you need a simple function, let's call it larger, just to see which of two things is bigger. Without templates, you're writing that exact same logic 4 different times. One for integers, one for characters, one for floats, and another for strings. It's a total maintenance nightmare, right? The dream here is elegant automation, writing that core logic literally just a single time.
Which brings us nicely to section 2, introducing C++ templates. Let's ditch that maintenance nightmare. Templates are the elegant solution C++ gives us to just wipe out this duplication problem entirely. So what exactly is it? A template is basically a single code segment. Think of it as a master blueprint. You use this one blueprint to automatically generate a whole set of related functions, which we call function templates, or a set of related classes, which are class templates. You write it once, and the compiler handles all the heavy lifting. Now, check out how this blueprint starts. You use the keyword template, right? Followed by angle brackets holding class type. Now, what's really cool here is how type acts as a formal parameter. You know you pass variables into standard functions? Well, with templates, you're essentially passing the actual data type itself right into the code. It's kind of a game changer. So let's move into section 3 and see this in action with function templates. Here is how that syntax actually applies to a function. By slapping that template header right above your function, you're basically unlocking a superpower. You can now take that formal parameter, type, and use it anywhere inside the function. Use it for your input parameters, use it for your return type, or even use it to declare internal variables right within the function body itself. It's totally flexible. Let's walk through a concrete example. Look at this maxT function. See that header? That t is basically a magical placeholder. The function takes 2 inputs, a and b, both of type t, and it promises to return a value that is also type t. The logic inside is dead simple. If a is bigger than b, return a, otherwise return b. The magic happens at compile time. Whatever data type you throw at this function, the compiler just swaps out that t for you automatically. And this perfectly shows the payoff. We feed it integers, boom, it outputs 20. We feed it characters, we get b. Floating point decimals, it spits out 3.9. We've got one single block of code successfully juggling ints, chars, and floats without even breaking a sweat. 0 function overloading required. How cool is that? All right, shifting gears to section 4, exploring class templates. So if function templates are your go-to for isolated actions, like finding a max value, class templates are the ultimate heavy lifters for complex data structures. The syntax is super similar, that same template header right before your class declaration. You'll often hear these called parameterized types. And that's simply because we're building generic classes that you can spin up later with pretty much any data type, whether that's a built-in int or double or some completely custom user-defined type. To really get why this matters, just imagine building a list data structure. A solid generic class like a listType needs a ton of operations. You got to check if it's empty, if it's full, you need search, insert, remove, sort. That is a massive chunk of code. You absolutely do not want to write all of that out for a list of integers and then have to write the whole shebang again for a list of strings. Class templates let you write it exactly once. Let's look at a really clear example with this point class. Say we want a class to represent an XY coordinate on a graph. Instead of locking ourselves into whole numbers or decimals right now, we just use our generic template type t. So both our private x and y properties are defined as type t. And notice how we define member functions outside the class too, like that setXY function? It gets its very own template header and uses t for the incoming values. Now, when we actually go to use this generic class in our main function, we just have to tell the compiler what t actually is. First, we spin up an object called p1, and we literally just tell it in those angle brackets, hey, make this an integer point. Then we make a p2 object, explicitly saying it's a double point, and we pass in 3.5 and 6.6. We've got two completely different objects, all spun up from the exact same blueprint. And the output proves the magic is real. We get our integer coordinates 10 and 20, and our double coordinates 3.5 and 6.6, all running flawlessly across totally different variable types. I don't know about you, but seeing code run this cleanly and efficiently is just incredibly satisfying. Finally, let's look at section 5, compiling template code. Okay, before we wrap up, there is one crucial quirk you need to know about how C++ actually compiles this stuff under the hood. Normally, you split things up, right? Class definition in a header file, function definitions in an implementation file. Well, standard procedure kind of hits a wall with class templates. See, passing a parameter to a normal function happens at runtime, but passing a data type to a template, that happens at compile time. Because the compiler literally cannot build a template without knowing the actual data type from your main code, you usually have to group the implementation and header together. The easiest fix? Just drop your class definition and your function template definitions right there together in the same header file. Definitely keep that in mind when you're setting up your projects. And that is a wrap for this explainer. You are now fully equipped to use formal parameters to write universally adaptable functions and rock-solid parameterized classes. So with templates literally turning your data types into parameters, what complex data structures are you going to simplify next? Take a hard look at your own C++ projects and hunt down those duplicated lines. Thanks for hanging out with me today, and keep coding smart.